Should be okay now, right?
That's right. Yeah.
Okay, so my name's Mark Simpson. I'm going to be talking to you today about Astrid, the need for it, how it works, and the comparison to other occultation acquisition methods. At the end of the presentation, there's going to be a Q&A. If you have any questions along the way, feel free to put them in the chat, and I'll answer those at the end too. Okay, so I
Recording
started.
in progress.
So I started occultations March 2023, so just over a year ago. It's been kind of crazy since then. So I did my first occultation on the 19th of March. It was a 17-kilometer diameter. It's quite a bright star, and it was only a 1.5-second occultation. I got informed about it the same day, basically in the morning, and I had no clue what I was doing. I had to find out pretty rapidly. So first thing I needed was a camera. I didn't have one. My main camera had been sent back to ZWO to be repaired, so I kind of had to cobble together a planetary camera that I had. I had zero experience, obviously. I had to find the right equipment, and I found out that none of it was ideal. I had to figure out the method of actually recording the occultation successfully.
Fuck.
And I found that the best practice was using an older camera with GPS timestamp, which I didn't have, didn't want to buy, and I was going to take time to get anyway, and I wouldn't be able to get it the same day. So I deployed. I deployed with an SCT. At that stage, I didn't realize you wanted to have a wider field, so I zoomed. I got as shorter focal, as high a focal length as I could. There were 4 observers on that event, and I ended up with the data. So I ended up with the data to process it for that event, and we had a variety of setups. So one of them was an iPhone with screen timestamps. Another one was an iPhone plus an Arduino GPS flasher. There was one QHY GPS camera, and I was the ZWO planetary cam and an iPhone flasher. So the following week, I think somebody's left their microphone on. I don't know if they want to switch it off. Anyway, the following week, I had to learn the software to analyze the light curve. I had to figure out how to accurately timestamp all the videos, and obviously there were problems with all the acquisition. I had to submit the reports, and it was kind of a bit of a mess, essentially. So the problems that I encountered were cell phones have variable frame rates, which isn't very useful to get accurate timing. The QHY required a firmware update that was problematic to install. The QHY required the firmware update to be the device to be sent back to them to install the update. And there's all sorts of version issues as well with firmware, which can cause problem with those devices. One person had a EV scope raw video, which they couldn't get converted. So at that stage, with EV scopes, you didn't own your data. So you had to send it off. You had to basically ask them to dig it out of the cloud and convert it into a raw video. That guy asked a number of times and didn't get a response from EV scopes. Essentially, that all we had for that cord was the recording he'd taken of the screen at the time via the iPhone, which again has variable timing. The timestamps on the video are only accurate to 1 second, and for the flasher on the iPhone, the best case was 50 to 200 milliseconds accuracy if there was a good cellular connection, and who knows what time the cellular provider was kicking out for the phone to sync to, right? That could have been off too. Also, the quality was poor video quality due to compression, and the other thing was some of it was saturated. Some of the signal was saturated as well. So basically, pretty poor timing, right? I didn't know any better, but I immediately saw the problems when I started analyzing the data. So other problems that we encountered was the software is really complex. You're juggling a lot of things. I needed extensive help to figure out how to get things like PyMovie and IOTA working. I'm going to forget all this the next time, so I had to take extensive notes. It was it's very difficult to get right, and it's expensive hardware for single use if you're going to get the custom hardware for it. And the Flasher app, so I didn't have enough. I was warned not to get the flasher too close to the tube and saturate the sensor. So I was conservative, and it ended up the flasher signal wasn't detected because there wasn't enough brightness to detect it. So, sorry, I just pressed the button here. Let me get started again. There you go. So what's the result of all these problems? First of all, it impacts the quality of the scientific data. We've heard it time and time again. Dave Harold's going to be speaking about it later as well, no doubt. We're getting data coming in that's essentially is inaccurate, and we don't really know what the accuracy of the data is either, right? It can vary, so assumptions had to be made. Do we use the data, or do we not use the data? Do we derate the data? It raises a whole bunch of problems, right? Is this observation correct? Is it meaningful? Is it discovery? It may not be because the data's not great, right? It results in missed opportunities. If it's difficult to do, then people are going to miss events. They'll try and get set up, and they'll miss the event because things went wrong, right? It's really a barrier to adoption. If you want to get somebody new into this, it's significantly difficult. We all want good quality data, as much data as we can get, but we're putting all these barriers up for people to adopt. There's a lot of learning that has to happen to actually start doing it. It's also a barrier to the younger generation. A lot of people, sorry, I just want to mess my slides up again, just bear with me. Apparently the back arrow goes back, restarts. So it's a barrier to the younger generation. There's a lot of software and a lot of astrophotographers out there now who could be utilized, but they expect the software in a certain way that makes sense to them and that's easy to use. There's certain paradigms of usage now that are out there with the various devices that you can buy that kind of solidify a certain approach that people use to acquire data. And if it can fit into that mold, then essentially we'll be able to get more people on board who are familiar with those types of systems. Analog's going away. Analog sensors probably went away like 10 years ago. They're getting more difficult to get. They're getting more difficult to source. It's not going to get any better. I mean, even security cameras, which was really the last domain for analog sensors, the digital sensors now match the analog sensors. So even in the security camera area, analog's going away there as well as they convert to digital. The other thing is time-based accuracy. All this is about time. If we can't guarantee the accuracy of our time base, then how meaningful is the data, right? We're going to have to move it in time to fit, and that might result in a different shape of the asteroid, for example, or the turfing of a double star, an observation that's potentially a double asteroid, right? So the wish list. So I kind of looked at this and figured, well, what can I do about this? I have a skill set to build certain stuff, and figured that a lot of these items could be addressed, but it would need to be more of a coherent type integrated system. So I wanted something that was cheap and easy to repair. I wanted something that could do double duty. So I'd really like it to do astrophotography as well, and then I can actually do something else with it when I'm not doing occultations. Decide to make a few of them and make them easy for people to deploy. I wanted it to do all the heavy lifting, so the plate solving, everything needed to be done in that one unit. I needed to be able to have switchable cameras. So there's certain camera requirements for occultations, there's certain camera requirements for astrophotography, right? We might choose a different camera for each situation, right? I wanted something that was like the ASI Air, Nina, Stellamate, Astroberry, essentially something that followed the same paradigm that people were used to. Needed to be global shutter for occultations. Some of the occultations we do are using rolling shutter and really You know, you're going to get different timing depending on which line you are as you go down the screen, because global shutter is essentially one snapshot at a particular point in time, and rolling shutter is it reads the line off as it goes down. So the time on a star at one point will be different than the timing on a star further down, right? The other thing, we need accurate timing, and you know, to remove any debate of timing, then make it as accurate as it can be, right? Need to be a single unit and connect via wireless. Essentially, if we can remove the display, we can remove some of the weight. And by connecting by wireless as well, then you have the option to stand up and change things without having to bring a table to put your laptop on and things like that, right? Or crouch down on the ground. Also, we need it to be easy, consistent, and have quality assurance on the hardware, so we know that the timing is correct. And also include all the software in the OS. And this is essentially it. This is Astrid, and it stands for Astrid Imaging Device. And this is one of the original ones. So it's a self-contained unit. It contains a Raspberry Pi 4, which is essentially works as the computer to run everything. It includes a camera, it includes the time stamping, and it includes all the software. Plugs straight into the eyepiece. So this is a 1.25-inch adapter. The wireless connection over VNC or remote desktop, which you can run from your tablet, your laptop, your phone. It doesn't need to be a particularly, you know, a particularly strong machine. It can be like an older machine from, you know, a number of years ago, because the software requirements aren't, you know, the processor requirements aren't high to run VNC. If you're using a phone, you can use a phone at a pinch. I have an iPhone Max, which I use on it if I forget to bring the tablet for some reason. It's kind of nice little backup. It's not the most pleasant experience, but it's adequate if you get stuck. But you know, just a smaller laptop, smaller tablet, or a larger tablet is ideal because you can just hold it in your hands, and you know, it's easy to carry around. But you can also bring a laptop too as well if you want to control it with that. It's a bit overkill, but you know, you can do that too. It works for occultations or astrophotography. So you know, it's the ideal device for occultations. It's not designed to be the perfect device for astrophotography. You know, there are more expensive sensors. I mean, you can spend 6,000 on a full frame sensor, for example, and some people do that. But it's, you know, it's equivalent to a device that you may have had like 2 or 3 years ago. And you know, for the beginner astrophotographer who doesn't want to spend a lot of money, wants the complete system working, it's cheaper than the other options out there to get started with that. So so it is useful, and it can actually do some reasonable astrophotography too. It's got an app designed specifically for occultations and astrophotography. And on board, there's a custom timing board I built called OT Stamper, and it's global shutter. So this is one of the recent batches of the OT Stamper boards that I put together on the right-hand side. So we're kind of into production here. We're making quite a few of them. They're selling out quite fast. So it's got highly accurate timing, which is based on a frame pulse that actually comes off the camera sensor. So there's no flasher involved at all. It's written in Python, so it's easy to change. As much as I hate Python, I decided to use Python because it's often considered to be easier for others to change things, and if they need to. It's open source. That was another requirement. I wanted open source purely because, you know, something ever happens to me, or you know, the project shouldn't die, the project should continue, and open source is a good solution to that. And also it gives people you know, a guarantee that the software lives and the product lives, you know, lives on and doesn't get taken away. It has an onboard 12-volt supply, so it will convert the voltages it needs, and you just power it with a standard 12-volt supply. that you'd use for astronomy. So typically, I tend to recommend the lithium batteries. They're quite lightweight. They're not really that expensive now. Often they're the same price or cheaper than a lead acid, and they're better in the cold. Lithium phosphate is the way to go because it's safer. But you can also use lead acid as well if you want. What I don't recommend, and what we have had problems with, is the cheap 12-volt power supplies that contain a few small 3-volt lithium cells, which are called power banks. Generally, they specify the current they supply, but in practice they don't supply the current that's needed. And there's often the current they suggest it can supply is done at a different voltage than 12 volts. So avoid those if you can. Just go for the lithium or lead acid. The one exception to that would be the Celestron packs. Some of the Celestron packs, not all, but some of the bigger Celestron packs can supply the requirements that are required and are good. It has switchable camera sensors. Most people aren't switching these camera sensors over, but there are other options if you're really into astrophotography that will give you slightly better results. And also it will handle mono or color. At the moment, we're just shipping it with a mono sensor because it just makes a bit more sense for occultations, but it will actually handle a color sensor as well. So this is one of the new cases that I 3D print. So it has device has GoTo. So if you have a mount that supports GoTo, you can do this. You got plate solving. You got polar alignment. If you've got an EQ mount, you can polar align. It does like a 60-degree move, and will actually tell you how far off you are, and then you can adjust your mount and keep plate solving, and it will iteratively tell you until you get down to say 2 arc seconds or something, or 2 arc minutes typically. It's designed completely for the task. It has automation and planning. It also syncs to OW Cloud, so you can download your stations from OW Cloud. Reduces user error, which is the other issue. Is there's so much going on, there's so much errors that can occur. So we really need something that reduces possibility of user error. It's got an audit trail as well, so we can take any video and we can actually audit that and figure out, was there anything wrong? For instance, did the GPS have a good signal? Right? And it does report filling for you as well with the North American report forms. So that essentially removes errors that the reviewers will typically see. For example, what Norm was discussing yesterday about pretty much every field can have an error. This helps remove it if you use the tools that are available in Astrid. The other thing as well, it always does raw data. There's no compression because we don't want compression because it messes with the data. It's frame triggered. That's very important for the timing. So in other words, when the frame actually occurs, it's time stamped by the stamper board, and we know the accuracy on that time stamping, which I'll go to in a minute. It's got saturation detection, so you can see if your star's saturated. It implements a custom file format called RAVF, which includes metadata about the observation. It calculates exposure for the events. So there's a tool in there where you can actually figure out, is your exposure, you're choosing the right number of frames per second to get the maximum signal, and the best timing, but you're not saturating. And this is kind of like an overview of the design. So basically, you've got a computer that talks to the camera and that talks to the OT stamper board. And then from a software perspective, there's a general functionality, astrophotography functionality, and occultation functionality. So these are some of this in fact is one of the first Astrid versions that I was experimenting with. So back then it was a resin case. We now switched to a 3D printed. There was a 3D printed resin case. We now changed to a 3D printed FDM case, which is quicker to produce and less problematic, so it ends up being, you know, less onerous on me to make the cases. You can see it there hooked up to a Red Cat 71. The original version actually had an LED you can see in here in the bottom left corner. I was just using that at the time. It just acted as a simple GPS flasher just to verify that all the timing was correct. Since then, it's not being used because I've got other ways of verifying that anyway now. Okay, so this is a little video of the first one. There's a fan on the back, so you can see the GPS connection going in there. Now, which camera sensor? So there's always a lot of discussion on the list about, you know, this sensor is better than this because it has this much QE. You know, I would argue it doesn't really matter. You know, sensors are so good these days. If you have a modern sensor, they're all fairly similar. You know, what's of more interest essentially is your noise level. But I'll go into QE in a second. But Astrid is up there. I mean, Astrid beats a lot of them. For example, it beats the QHY174 GPS. You know, across the across visible wavelengths. It's actually a Gen 2 sensor, whereas the QHY174 GPS is a Gen 1, for example. But I did a fairly extensive comparison. I kind of wasted my time essentially because at the end I just concluded it doesn't really make much difference. So, but if anybody ever needs to see this list, I'm happy to send it to them. It kind of summarizes all the sensors, the technology that's used, the interfaces, things like that. So the sensor I settled on was the IMX296 LL mono. So it's a 1456 by 1088 pixels, so 1.58 megapixels, 3.45 micrometer square pixel size. And it's got a really nice low read noise of 2.2 electrons. Dark current's reasonable as well as 3.2 electrons per pixel per second. Full well capacity is 10.6 KE, and the peak QE is 68% at 550 nanometer, and the maximum exposure time is 15 seconds. And also, it doesn't have an IR cut filter, so if you want one, you can put one in. I tend to prefer not having it in because I want every photon that I can get, but you can put one if you want one. And here it is compared to the IMX174L, which is the QHY GPS. And you can see the 296 is 10-bit, the 174 is 12-bit. The 174 is a bigger sensor. It's 77% QE, and the IMX, the Astrid one, IMX296 is 68% QE. But you can also see that the 174 GPS has getting on for close to double the read noise. So here's a comparison between the Gen 1 and the Gen 2. So when you look at QE, peak QE, it's always peaked at a certain value, right? So on the right, we've got the Astrid one. The red line's the peak QE. You can see the peak QE on that is 550 nanometers, and on the 174 GPS, it's 510 nanometers. But you'll also notice that on the left, the IMX 174 is quite a sharp peak, and the Astrid is quite a flat peak, right? If you look at the area under the curve, which essentially is, when we're looking at a star, we're looking at all frequencies of light. We're looking at white light essentially, and partially into the infrared as well, maybe a bit into the UV. Then the Astrid one actually performs better because the area under the curve is higher. So you're actually getting more photons on the second generation Pregius sensor than the older Pregius Gen 1 sensor on the 174. Now, I'm just giving an example of how the QE is better. Does that make a whole lot of difference? In reality, no, it doesn't make a lot of difference. All the sensors now, are typically between 60 and 100% QE, and but 60 and 90% QE. There's actually not that much difference in the grand scheme of things. So it doesn't really matter, is what I'm saying. But it is slightly better than the 174 GPS. So here we got 3 Astrids running at our local astronomy club one evening. On the left, there's one hooked up to a 9.25-inch Edge HD Celestron. In the center, we got an Orion 80mm. On the right, we got Bill Young's Nexstar 6 SE. That was during some of the early testing we were doing back last September. This is one of our stations from an 8-station deployment a few nights ago. Each setup takes about 5 to 10 minutes, and we recover them after the event on the way back home. This shows up one of our setups close in. It's a cheap Orion 80mm. It's a mighty MIDI essentially. There's a lithium battery at the front, an Astrid to handle all the computing. There's a camera and the recording software in there. GPS antenna can be seen on the left. That's that little square puck. And this is a mount I designed called the T-slot Broughton mount that's based on the concept of John Broughton's designs. But this one's made out of 3D printed parts and T-slot. And this is also an open source design that you can download. I put the link down there for it. This is another setup we have. So this is a 6-inch 150p Skywatcher flex tube. And this setup has go-to. So, you know, some of our setups are manual pre-points and some of them are go-to. And the go-to we can use for pre-point, or we can use a go-to just to go to the target. This is it hooked up to the club's C14 the other day. You see Astrid on the back there. And then this is kind of nice because it gets quite cold up here in winter. We're in Canada. So we were streaming the output over AirPlay on a big screen in the warmth of the clubhouse. Eric's son, who's in the picture, even has a microwave popcorn whilst we watch the occultation from the comfy seats. The point is here that Astrid can be run on a variety of scopes, both with and without go-to, and of various sizes. Essentially, we're using VNC to connect, which means you can operate it from your vehicle, for example, or inside from the comfort of your home. You don't have to be sitting out there crouching down in the cold. So here's some of the astrophotography done with Astrid. So on the left, we got the Elephant Trunk Nebula. This was done with a Red Cat 71, which is 350mm focal length and 71mm aperture. So that was 30 minutes of stacking. On the right, we've got Supernova. Sorry, it's close, covered my screen here. Supernova 2003 IXF in M101 from last year. So that's a 60-minute exposure. That was also on a Red Cat. And then this is with the, so that was with the HQ. Yeah, that's with the HQ camera, which is a color camera, with the global shutter camera that ships with Astrid. Then we got, this is a M3 for 12 minutes, M101 for 12 minutes. The one on the, you probably heard me say it a few times on the forum, that forest fire smoke isn't a problem to observing. Cloud obviously is, but forest fire smoke is basically transparent in the infrared. So even if you have heavy smoke, so heavy you can't see a single star, most of the time you can still see through it in infrared. So this is 25 minutes with heavy forest fire smoke, and then the Elephant Trunk Nebula with forest fire smoke as well. It does attenuate it a little bit, but it's still workable, certainly workable for an occultation. And these are the OTE stamper boards. So this just shows the boards. I make all of these. This is one of the earlier versions. And what's the timing accuracy? So getting accurate timing is critical. So this shows the jitter on the timing, essentially, right? How much the jitter varies. And this jitter, most of it is actually due not to the GPS, so it's actually due to the processing, because it takes so many CPU cycles to process it, and this jitter is just like the variance of about 2 or 3 CPU cycles. I've got it as optimal as I can, essentially. So the worst case timing that I quote is 1.25 microseconds. So that's you know, that's 10 to the power of -6, right? But in practice, as you can see from the jitter, most of the timestamps are actually accurate to about plus or minus 250 nanoseconds, so 10 to the -9. So it's more than accurate enough for anything we would use, even for near-Earth objects as well, right? The GPS uses PPS, which is pulse per second, which is transmitted from the GPS network. So timestamp accuracy I just discussed. There's a forgiving 12-volt DC power supply in there. So yes, you can short something inside the case. You can put the power out the wrong way. You can even over voltage it to about 18 volts and it will survive. Obviously, there are limits. If you're going to connect up to mains power, you might not have a good experience. But it's good. It's well designed, and there's a fuse within the OT stamper board as well. There's a switchable fan. I didn't really need to do this. The fan turns out to be quite good, but maybe if you were, say, using a big massive dob and you're going to a very high focal length and you wanted to reduce any chance of vibration at all, you can switch the fan off automatically during the acquisition. There's no firmware cables or anything like that. Essentially, all the firmware updates are done via the Raspberry Pi. And this is how I build them. This machine is a machine I built called a pick and place. And yeah, and basically every board goes through this that you've seen and it's on the store goes through this process. So I had to put solder paste via stencil on the boards first, and then all the components get picked up one by one and placed on the board. So it's just picking up a looks like a 0603 resistor here, which is about 2 millimeters by 1 millimeter. Takes it to the camera, it takes a peek at it, figures out at what position it is on the vacuum head, and then it puts it where it lives. Then it goes to the next one. It advances the feeder the next position. You can see the tape advancing there, and you see the component in there. This one's a capacitor, so it picks up the capacitor by vacuum, lifts it up, takes it to the camera, checks the position on the nozzle, adjusts the orientation of the nozzle for the position it's in, and then places it on the device and releases the component. The components stick because the solder paste is sticky, so it comes off the nozzle. So case options for Astrid. So basically there's two form factors. The first one is the original format that's for refractors, SCT, Newtonians and Dobsonians, and everything is in one unit. That's this is the one that is the preferable one to get because it's just a single unit. If you have a situation for requiring the camera separate, for instance, if you're using a prime focus setup, or you're using a Hyperstar and an SCT, or smaller Dobsonians where you're concerned about the weight near the top of the where the focuser is, right? Then you could use the prime focus. This is the mini display. So there's two Wi-Fi modes. You've got a hotspot for mobile deployments that Astrid creates itself that you can connect to, and also you have link quality. So when you're connected to your home network, then you want to know how strong the signal is. So we've got a link quality indicator here, which is 91%, which is quite reasonable. The little screen, the little line at the top that says Wi-Fi in the network gives you is red, yellow, or green. Because of the color on the camera that I took the picture with, this is actually green, although it looks like it's yellow. But you're typically looking for a yellow worst case or a green line here. If it's ever red, then you just don't have enough signal to be able to reliably connect. So don't use it. Fix your network. Get closer to the router, for example. The yellow buttons on the left allow you to switch between the networks. You just press one of the buttons for about a second and it will switch between hotspot mode and home network, or back to hotspot mode again. So what do you need? So you need an Astrid, first of all, to do occultations. You need 12-volt power, and you need a laptop, tablet, or a pinch and iPhone. But you only need one of them. If you have multiple Astrids, I just have a tablet and I just take it around. I deploy one and then I'll take it to the next one and I'll take it to the next one. You don't have to leave anything at the site. You don't have to get one for each device. And that's essentially it, okay? What you don't need is a variety of software like ASCOM drivers, SharkCab, etc. to install or maintain. You don't need to do OS updates all the time. Windows, Joan discussed yesterday about OS updates, all the things you have to do to stop it giving you alerts and disrupting your acquisition and things like that. You don't care about any of that with Astrid. You don't need to leave an expensive laptop in the wild and then hope it stays there. Hang on, I just pressed a button here. I'm not quite sure. I seem to stop my... There you go. You don't have to be in attendance for the occultation. Go to bed, get some sleep. It's very, very good to get sleep. You don't need star charts anymore. You don't need to turn up at a specific time for your star chart for a pre-point, and then when you miss it, try and find which other star, and suddenly you've got 5 star charts with different stars at different times in case you turn up late. All that goes away. You don't need a GPS flasher. You save time. You no longer have to spend a long time finding your target. You've got an automatic site download from OW Cloud, so you can download your stations. Saves you having to enter the details. It fills the reports out for you. You can generate Finder images as well. So that speeds up your time in analyzing your event in PyMovie and IOTA. You reduce a lot of errors. So essentially there's zero chance of any zero timing error. You can trust the timing 100%. If you have a frame, it's got a timestamp, and that timestamp's correct. You've got zero chance of entering a wrong array or deck or start or stop time if you're using the provided features. It does the auto report feeling. It will get the GPS location correct for you. There won't be any error. It will get the target correct for you in that report form. Again, no error. It will get the event details correct. It will get the scope details correct, and it's going to get the start and stop recording time correct. And if you use IOTA, it's going to actually fill in the DNR times for you as well. So it does a lot of the heavy lifting for filling out reports. And it's designed to, so from a design point of view, and this is something I've been fairly careful about, and if I get any new feature requests, it always goes through this kind of analysis to make sure it fits in with the current design view. So it does what it can for you automatically to reduce your workload and an error. It's very important. It reduces the requirement to input data. So I don't want people typing stuff in because that's when errors occur, right? Nothing to type in, no error. It speeds up and simplifies the occultation targeting. It also provides confidence you're on target. So you know when you're on target, and there's no debate about that, right? You will get that acquisition unless you were to do something like, say, kick the scope or something like that, right? In which case you just set it up again. It presents only the information you need to be aware of, and it presents it clearly to you, so there can be no confusion. It catches any potential mistakes the user may make and clearly prompts for the problem, and so you can address it rather than letting you find out after you've done the occultation. It won't do anything silently that might impact the user's observation. So if there's any chance of it actually messing up your occultation, then if it prompts, it's going to prompt for something, it's not just going to do it under the hood and not tell you about it. It will detect deployment position changes. So if you plan to be at one particular site, then it's clouded and you end up driving another 100 miles to another site, it will adjust for that, and it will adjust the timing for that as well to account for that movement, because it's going to detect that you've moved position. Astrid actually has the ability to calculate paths internally and uses that. It produces a full audit trail for the recording as well. So anybody can go to that recording at a later date and say, yeah, this is what happened and this is where it was and this was the result. You just have to send them the video file and maybe the log file if you want as well. So what are we at? 38 minutes. So this is a video I made on YouTube that illustrates how Astrid can use to record an occultation with a simple manual mount. Like this setup can easily record events down to mag 12. I'm going to just play some of this. I'm going to skip through some of it just to get an idea to speed up a bit. Hi, I'm Mark, and I'm going to be talking to you today about pre-point asteroid occultations with Astrid. Astrid calculates where the star will be at the time of the occultation and directs you to that point. You iterate until the error to the target location is acceptable. Astrid does all the calculations for you. You can throw away the star charts. The star will drift into the center of the field of view at the mid-event time. You no longer have to turn up at the site at a certain time to find a certain star. Let's do the 3-minute pre-point. This step is optional, but it saves you about a minute and a couple of iterations on site. I set the course altitude using a level app on my cell phone. Then in the field, I can go straight to the fine adjustment. Tonight, asteroid Porthan 2333 is occulting Hipparchus 19853 at 3 a.m. The main track is 3,000 kilometers away, so I've elected to use this as a test whilst I'm sleeping. Astrid is positioned roughly southeast and is plugged in, powered and ready to go. First, we need to connect to Astrid, and I use VNC running on a tablet for this. One tablet or computer can handle multiple Astrids. Now we start the Astrid app. Elapsed time can be seen top right. On the first screen that's presented to you, you can change the colors for Astrid and the settings. Astrid has plate solving, so it always knows where it is in the sky. It's designed to reduce the workload and errors during acquisition for occultations. We switch our object database to occultations, then list the occultations we have stored, then select the Porthan occultation. We are now ready to pre-point the occultation, so I hit the pre-point button. Then I hit the Photo, Solve and Sync button for the first iteration. The photo has been taken, and now it's plate solving. Plate solve is complete. We need to move 4 degrees left and 36 arc minutes up. So I adjust the mount. Then hit Photo, Solve and Sync again for the next iteration. I overshot, so now I need to move 3 degrees to the right and 27 arc minutes up. Photo, Solve and Sync again. Now I need to move 23 arc minutes up and 3 minutes to the left. Now, at this point, you could actually call it done. It's good enough. Next iteration. Whilst I'm doing this, I'm looking at the positional error as a percentage of field of view. I want the error to be less than 20%. But we have a bit of a competition where me and Bill are trying to always get as low as we can to reduce that error. It's now 13.5%, which is good enough. I could stop here and just click auto record. However, I'm going to see if I can get even better. And now the new version of Astrid, the later versions of Astrid, 4.7%. Later versions of Astrid actually have crosshairs as well for the target. And I've now reached 1.5%, which is very high precision. Next, I hit cancel and set up the auto record. However, I forgot to check the frame rate in game, so I'm just going to go back and do that. Note that despite the light being on outside and light ingress into the tube, it's still plate solving fine. I settled on a frame rate of 10 frames per second with auto stretch on. Note that raw data is only ever stored to files. Stretched data is only for display. Now I set auto record and head off to bed. Astrid will record from the start time to the end time, and the star will be centered at the mid-event time. Astrid must always be shut down properly, so I select shut down after recording to save battery power and to make pickup faster. Lights out and wait till tomorrow morning. Here's a speed up of the star field as it moves in front of Astrid. It's now morning, so cap the scope, remove the power and collapse the mount. The USB drive contains the video data, and we'll analyze this on a computer using PyMovie and IOTA. Here's a video of our occultation. We don't expect this to be a positive because it was so far from the track, but there could always be a satellite or double star. This is an image of the star at the mid-event time. As you can see, it's centered. Here's the resulting light curve. Please thumbs up and subscribe. Okay, so now I'm going to do a live demo. So that kind of gives you an overview of how you do a pre-point. But now I'm going to do a live demo when I can get my screen to, there you go. Okay. So I'll just minimize this. So what we're going to do here is, so you've probably seen this a few times now. So we've got real VNC viewers. So we need something to connect to Astrid. So I've got my Astrid connected to my home network at the moment, and I'm just going to connect to Astrid. So I've got a Astrid 5. So I'm just going to double click on that, and that connects to it. First thing it asks for is the username password. The password is always IOTA, and the password when Astrid is in hotspot mode is IOTA or IOTA because it needs to be 8 characters. But you can always change the password if you wish as well. But by default, when this ship, password is always IOTA. So I'll just click OK. And it's now connected. So this is your standard Astrid screen. We've got the ability to change the Wi-Fi connection details. We can shut it down. We've got player and Astrid app, which are 2 things we need. So, and then we've got the USB drive. So that's the Astrid USB driver where the data is stored and your plate solving files and things like that are stored. And you can eject that and put it in a desktop, for example. And then we got, this is for the mini display, you can ignore that. And then we have a tools folder, which has various things that are useful to Astrid, like qualifying the drive, diagnostics, upgrading Astrid, formatting the USB drive, that kind of thing. There's also a lights out button where you can switch the lights out as well on the device. So launch Astrid here. So the first thing Astrid does when it launches is it gives you the ability to change the settings. So if there's anything, so first of all, you can choose what scopes you have, what your setup is, so you can have multiple setups. I'm going to use a simulator today as it's daylight and I've got it inside on my desk. And you can change your colors as well. So if you want red, red everywhere, then you can do that too. So you've got settings. So you send various things to do with the configuration for the camera. Default gain, default exposure, for example, you can set here. You can set up your mount here as well, so it'll handle EQ, alt-as, go-to, non-go-tos, mounts that only track and do nothing else as well. These are your plate solving details. This is where you put details about your telescope essentially and the focal length. Now I'm not going to click on the server because it'll give me my password for OW Cloud, and I haven't figured out how to change it on the website, so I won't click on that. But basically, in there you fill in your observer details like your name and your OW Cloud details for syncing. And here you put your telescope details, so your aperture and what type of telescope it is. This gets filled in your North American report form automatically. And then just general things on there. I've got it fuzzing the GPS at the moment, just so I don't dox myself. You can get it to power down automatically on low voltage, for example. You can denote what the center marker looks like when it does plate solves. And you can also denote what your limit is on annotating stars when you're looking at exposure. So those are the settings. So start Astrid. So the way it's been designed is everything is presented to you in one screen, essentially, right? And anything that needs some interaction is a dialog box that pops up in front of it. So if you look here, the first thing is I got everything on the screen. So this is where I'll see any photos I take. Anything that affects what I'm operating on, so essentially the task, is defined here. If I'm looking for objects, all that is in here, this panel. Anything to do with the display is indicated in one of these 2 panels. This is just all mount stuff. And then these status buttons down here, right? So all of these you want to be green, with the exception of the site button, which can go to orange, and it's not an issue. If you get red or orange on any of the buttons, then you can't acquire data with automatic recording. You can with manual recording, but it's probably in your interest to make the buttons green. Most of these will be green all the time, unless you have a bad GPS signal for some reason, like you got it indoors, or you're not pointing at the sky, or you've got a metal can over it, or something like that, right? So this one's red, so I'm going to just click on that, and I'm going to just click on update site and mount, and you can see it's gone green. So when you go to a new location, you're going to have to do that. It's going to be red, and you're going to want to click on that update site and mount just to update the location to where you are now. Okay, so essentially it's traffic lights. So just think of a traffic light. If it's green, it's go. If it's red, it's stop. If it's orange, it's caution. Now with the mount, you can move the mount by using the mount arrows. So you can see my mount, my RA and deck changing as I use the mount. And you can change the movement speed as well, depending on your mount capabilities and your tracking rate as well. And if you did something wrong and you want to stop the mount moving, just click on the stop button. So let's fake a picture here. So I'm going to fake a picture. It's daylight. If I was to take a picture now, it's probably going to point at my ceiling if I give it a reasonable exposure. So let's just drop the exposure here. 0 and turn, sorry, let's 0. Let's do 1.0 for the gain and 0.01 for the exposure. I'm just going to switch off the stretching here. So there you go. So we've got a picture here. I've got the studio lights on, so it's fairly well saturated, but it gives you an idea. I've got stretching up here. This is contrast limited adaptive histogram equalization, which is kind of like a auto stretch. So you've got various settings for that. You can also use min max. Min max goes between 0 and 255 as the values. And you can also specify a custom min max if you wanted to. You've got a button to take a photo, you've got a button to plate solve. So I'm going to set this to 0, because when I have it in 0 in simulator mode, I can actually pull up previous images I've taken with stars in. So I'm just going to take a photo here, and then I'm going to click plate solve. And I'm going to go to photos I've taken from previous events. And let's pick one here. Let's pick, you create this one. So it loads the image. This is not a great image, so we'll see how this plate solves. There you go, it's plate solved. So there's not the best image there. It looks like it was a bit out of focus, so I was exposing quite shortly, but it has actually plate solved it without issue. And you can then sync the mount to its current position that plate solve is, and then go to the target, or you can just sync it. And when it plate solves, it gives you the focal length, the field of view, stuff like that. So now you want to do an occultation. So let's do an occultation. So I'm going to pull up here, find the right screen. So we're going to use a Haristo search from yesterday they implemented. So I'm going to do an occultation at, let's say 7 this morning. So I'm going to add a station here. So I'm adding my station. And I think we're going to put it down near standoff. So let's add that one. So we've added a station here. Station has been added. Okay, let's pick another event. So let's do this one at 9:54 as well. So I'm going to add a station on AW Cloud. And this is by far the safest and best way to add stations and make sure you're getting the information correctly added. Okay, so now we go back to Astrid. Astrid's on the internet because it's connected to my home network, so I can now sync those stations. So I'm going to go add, and I'm going to go sync from OW Cloud, and I'm going to go OK. And it's going to pull in these stations that I've just added. There you go. So it's pulled in 3 stations because I had another one in there. And there they are, right? So let's have a look at this one. So it's already calculated the center time, the start time for you, the end time, and it's calculated the duration of the event as well, and the error in time, and it's used all that to figure out when it should start recording, when it should finish recording. So essentially it's ready to go. We've got that. So let's select that one. So first of all, it's detected, as I said, I'm fuzzing my GPS location. So the location is different. It's like I'm at a different site. And Astrid has detected that, and it's prompted me to actually update the start and end time to account for the difference between where I added the site and where I actually ended up physically to record the event. So I say yes. So you might not want to do that, for example, if you set a site and you're now at home and you're looking at an observation, but you're going to go out later and actually deploy at that site, for example. So it gives you the option whether you want to update it or not. So if I had a go-to scope, I could click yes now, it would go to it, and basically I'd be done and could start recording. I'm not going to, because this one's going to be a manual pre-point. So to manually pre-point, this is where you normally use a star chart. You don't need that anymore. I just click plate, solve, and sync. And it says it's in test mode because I'm using previous images, which is fine. Okay, and it's plate solved that previous image we have on the screen, and it gives me arrows to go there. You can get these arrows. This is Alt-Az arrows. You can also get a single arrow. You can also get RA deck deltas as well. And it's telling me, I'm off on the field of view by 2611%, which is quite high, but that's because obviously it's not a real situation. I would now move the mount that would be on target. We move it at 27 degrees and 6 degrees down. And it tells me how long it will take to drift through the field of view. So in the horizontal direction, it will take 8.29 minutes to drift through the field of view. And then after I'd moved the scope, or after I click go to, I would then just do a photo solve and sync, and you keep iterating until that error is below about 50%. If you want to get it below 10%, even better, right? You're just looking at that positional error in the field of view. And that's essentially it. Once you've done that, you'll find that this arrow here won't be red. It won't be red at the edge. It will be green and in the center roughly. And then you just click auto record. And you set the video rate first for auto record. So it's not in video mode. So it's going to prompt me again. This is an example of an error I've made, right? So it's prompting me, but it's to make sure I don't make the error and don't record it correctly. And it gives me the opportunity to check the frame rate as well. And I click yes, and then I just click start auto record, and you're set up, and you leave it and come back tomorrow. If you want it to shut down automatically to save battery, you can click that button. Otherwise, it will be still running when you come back. Just depends on what you want to do. Now, what do you do when you get observation? So I'm going to use Tom's observation for this. So Tom did an observation he put to the list today. So I'm just going to load that up because it's quite a nice observation. Gives an example. So when Astrid records it records a few files. One of them is the video file, which is .ravf. So I'm going to open that. First thing I see is I can't see anything. Looks like there's a star there. No, I can't see anything at all. Okay. So I'm going to stretch the image. So I click the stretch the image and I see the stars. And I'm going to plate solve this. So I plate solve it because we don't know where the target is, right? I want to see where that target is. And you can see it's marked on there, the target with crosshairs. Okay. So, so first thing I'm going to do, I'm just going to save as fits finder so I can analyze it later. And then I can have that star pop up in PyMovie, and I know exactly where it is. And then essentially, I'm done with that. I can shut down Astrid and then go off and deal with the observation. So I'm just going to start up PyMovie. And I've transferred these files from the USB key to my local hard disk. So the first thing I need to do is need to open the ravf file. And PyMovie natively understands ravfs. So we open that and we've got our screen on here. Do the usual PyMovie stuff, do the image contrast. There you go. Switch that off, and I'm going to open the Finder image so I know which star I'm targeting. So I'm going to use that Finder frame I just saved. There you go, and it's got the crosshairs just there for for the target. So it saves trying to figure out which star it is. I'm going to add a static fixed circular mask. So I just added that, put in target. I'm not going to bother with reference star right now because it's takes a bit longer and this it's just a demo. But normally you put a reference star on there. I'm going to add 2 target stars, 2 tracking stars. Tracking 1, tracking 2, tracking 2. Click mark so I can save my settings, and then analyze, and then it goes off. I'm going to click auto run IOTA, and there it goes, and then it goes with that observation analyzing it. Now, in the meantime, while that's downloading, when that's analyzing, when Astrid created the video file, it also created 2 other files. One was called a log file, which is an audit trail essentially, and I can open that. It contains every single frame that was taken is timestamped, and lots of information is provided in it. You normally don't want to need to look at this. If you look at the last line, it tells you all these should be 0 down the bottom. It tells you if there's been any errors. Okay, so if you happen to come back, you didn't see the error buttons, and most of the time they're going to be green. You don't really care, but if you think you might have got an error, then you can just check this log file to see if there are any errors on there that you missed. The other thing it creates is an XLS file. You just fill out your name on the USB key, and you basically the observer's name, the observer's email, and it will autofill the rest for you when Astrid makes a recording. So this is Tom's data that he sent through. So it's automatically filled out the year, the month, the day, predicted time, the asteroid name, the star, and it's filled out where you were, the elevation. It's filled out Astrid information. It's filled out your scope aperture, your focal ratio. It's calculated for you. He's got a focal ratio of 1.9 there. It's quite nice. The type of scope, and and information about the sensor. It's also figured out when it started observing and when it stopped observing as well, right? And the rest of this information gets filled out later. And it's put in there that the report was pre-populated by Astrid, so that reviewers can look at that and have confidence that the information here is actually correct and the user hasn't manually entered it and made a mistake. So how's this doing? So this has finished the analysis now. So we're going to just write this to just a folder I put here. So quick little get the right folder. Quick little cheat here is you can change this to all files, and then change it back to change it to all files. Select that and change it back to CSV file, and then it will create the CSV file with the same name. Click save, and it's going to launch IOTA. So click OK. Now the process is quite simple. We do just a usual IOTA analysis. So I'm going to do that here. So click there, do mark disappearance. Click there, do mark reappearance. Okay. And then we do, and it says there 1 drop reading. That's normal on the first frame because it has to do a frame time change to figure out which is the first frame at the start. So that's quite normal. So now we do find event. Event has been found. Red bar is to the right of the 3 greens. So we're good. Signal to noise is 6.7 on that. Quite nice result. Duration is 1.78 seconds. Now, click Fill Excel Report and select your XLS that Astrid pre-filled for you, and you can fill in the remainder of the report. So now it's filled in your disappearance, reappearance times, the confidence errors, the confidence bars, signal to noise. All that's left for you to do is if it's a positive, you're good. If it's negative, change that to negative. Change was this a miss to yes. And then you want to put in your observing location. So it's already got your GPS, so that's good. But you might want to put where you were. So let's put Lethbridge, Alberta, Canada, for example, right? Not that's where Tom was, but you get the idea. And then you want to put in your clouds, your stability, like, whether it's good seeing or not, that kind of thing. And then that's basically it. Your report's ready to go. Zip it up, send it. So it makes report filling significantly faster.
Mark, the status, the file type was ADVS on the form.
Okay, so I believe with that, I had to ask Tom. Tom may have used an older North American report form on that potentially. I'll look at that, or it could be standard. I'll just check one of mine actually.
Mark, I wonder if you could break now and review the list of questions in the chat.
Sure.
And select those that you think are pressing enough to address at this time. Okay. We're just a little behind, and I don't think the time is a problem for us, but if you could select those that you think are most apropos, that would be good. Thank you.
I can also pick this up later as well for the remainder if you want.
Steve Preston has been answering a few of those questions already as well.
So look, taking notes. Okay, what is OTE? So that's been answered. Can Astrid be used to time lapse, record a frame each second for 8 hours? Yes, it can. So you can do time lapsing. You can do an eclipse. I did the solar eclipse the other day. You can also do intervals for doing stacking as well and things like that. What material is a case made of? It's made of ASA, which is like ABS but UV resistant. There was an older resin case as well, but the ASA case is better and a bit more structurally, less chance of breaking it due to dropping and things like that. ASA has ABS and ASA has a kind of like slight flexibility to it. If you ever damage the case as well, you can glue it with acetone, but or just order a new case as well. The Astrid does not have a time lapse. Yeah, it does. It does have a time lapse, but it doesn't have interval between it. So you can say fire off 1,000 pictures of a certain exposure with no issue, but it doesn't have an interval behind it. That is something I've been considering adding, but it adds complexity and potentially confusion. So I've been a little resistant to do that, but might add it at some point. But you can also just dump intermediate frames as well, right, and achieve the same goal. Okay, what else we've got? Mark, record as low as Bill's got 12 degrees is the lowest he's got on there, altitude. So if you move Astrid, knows apartheid from an OW. Oh, okay, so that's a good question from Ted Swift. So yeah, if you move the Astrid, it has its own path calculator in there. So it will actually, when it's about to do the recording, it will actually, or when it loads the occultation, it'll actually look at your GPS location, do a path calculation, and if it's more than a second difference, because you've moved, then it will actually prompt, do you want to update the times? And you can update the times for the new location. It will tell you how much you've moved by as well, how many seconds you've moved by. So that does it automatically. What else we got on there? Is it limited in frame by Raspberry, or does the setup? So the USB key is actually the limiting factor on the frame rate because it's raw data. So at the moment it's 30 frames per second maximum. If I do region of interest, which I'm planning on doing later, I might be able to get up to about 60 or possibly 100 frames per second with a smaller area. People do occasionally push up to 35 or 40. You get a warning and you might end up with the odd drop frame. That's at your own risk, but 30 frames is reliable. What's the screen resolution? So the screen resolution of Astrid when connecting to it is a little bit lower than you get in your data. So your data is recorded at full resolution, but you get a kind of like a compressed, slightly cut down view when you're doing it. You can change the resolution of the screen. Probably don't recommend it. I think it's 1280 by 1024 or something currently. What's the screen resolution Astrid is connected to? Okay, what's the next one? Qualified drive script tells you the frame rate of the. So it's very important to get a good USB drive, and we've worked quite hard to qualify those drives. So use the ones we recommend. Don't use the ones we don't recommend because you're probably going to have problems. We'll update that list as new candidates come in. If you do get one and want to try it, then you can always try qualifying the drive and see if it's fast enough to actually write at 30 frames per second. If it isn't, then you can write at 10 frames per second or at your own risk. But yeah, USB drives, you want the ones that we supply. What else we got on there? What involved in donating Astrid to observing team in distant country sight and see parachuting in? Yeah, good question, Ted. So yes, it's possible. There have been situations people from start, like I trained a guy for 15 minutes and left him on his own in the middle of nowhere, and he got a really good occultation for his first attempt. So and it was close to sunset, so he only had 10 minutes to find the location with the plate solve. He managed to figure it out. So parachuting devices in, yeah, can do it. It might be better to ask him to set up the day before, just so it's a less stressful situation, but just to get familiar. But yeah, you could even do it on the day if you need to at a pinch. What else? We can stretch the screen to fit from Tom. Yeah, donating Astrid. Someone needs to pay cost of the Astrid plus shipping. Yeah. I'm thinking of the last mile issues, mailing Astrid to Nambia, so that gets implemented successfully. So how you sure if you're sending it to somebody abroad and you want to make sure it gets implemented successfully, pre-set up the event on there, do everything for them. Don't even worry about stuff like Wi-Fi and games set up to networks and stuff. Just use the hotspot, connect to it, just create them a set of instructions or show them some videos on how to do that, and the experience should be fairly seamless. Can the plate solver account for hot pixels that may occur over time? Yes, the plate solver is invariant of hot pixels. One hot pixel or even a number of hot pixels aren't going to make any difference at all. It doesn't need to see all the stars. It uses patterns to match. No, there's no rotation of Astrid in the eyepiece holder. You can do if you want. I generally don't bother. I just put it in there. Doesn't matter where it's rotated. If you want to maximize, if you've got a pre-point that's going to drift because you've got no tracking, then if you orientate it in the direction of the drift, then you're going to get slightly longer exposure than if you orientate it in the other direction. But can it improve on the horizontal banding, readout noise, bias correction? So I'm not quite sure what meant by this question. The bias is normal, as is same with all cameras, because we quite often aggressively stretch with occultations. It's more visible at high gains. It's more visible than if you didn't have it, but it doesn't really impact the observation at all as long as you're above the noise floor. In other words, it's more visual when you stretch. It's not really an issue as such. Fits. So fits is an option. I suggest RevF and PyMovie. However, if you're using something like Tangra, there's no support for RevF in there yet. Hound the authors of other devices, of other software to get support for it. I'm happy to assist in getting support in there when necessary. If you can output fits from player, if you need to do that to analyze it in Tangra. If you pre-point, it makes sense to maximize the time targets. Okay, sounds good. So what Astrid records to RevF. There was some debate about getting it working with the ADV format, but ADV didn't do some of the features that were required for Astrid. Didn't support the camera, and there was obviously there's work involved in changing the spec to support that, so it was easier just to create a new format on that one. What's the maximum focal length that's plate solving Astrid would work out? It'll work fine at 4,000 millimeters, no problem, and even probably further than that. Does it also make coffee and keep? No, it doesn't make coffee. It doesn't keep the observer. Well, it does keep the observer warm because you can stay inside, right? Is there a tool for focusing Astrid? You can use a batten-off mask for focusing. I often just eyeball it most of the time, actually. Batten-off mask is there, though, if you want it really good. What else? I'm not sure on the focal length. There is actually some preliminary focusing support in Astrid. At some point, I'll be putting on automatic focusing. Not sure if, okay, well, so Astrid doesn't focus, you have to, focus on Astrid does, full focus accuracy. Okay, I think if it wants to donate, yeah, dealt with that one. Astrid cost, so I think the price cost. Cost of issues to play having a bunch of these ready to ship to observers for temporary use to observe in important events. That one I don't know. You had to speak to Ted and Steve and Joan and David about that. So those are the questions now. What do you want to do? Do you want to? Is there any chance you have a bit of time left at the end, or do you want me to continue?
Well, are you done? I mean, you're pretty much done with your presentation, or?
Yeah, it's sorry, I overrun a bit. Let me just get rid of this. Let's see how many slides I've got left. Just bear with me. There it is. Okay, I'm on slide 41. So probably about another 10 minutes. What would you like to do?
Why don't you head through that, and I think we'll be all right with the time.
Okay, sounds good. Okay, I'll just put this back on again then. Okay, so we've done the live demo. Okay, so discoveries. We've discovered a binary asteroid 2532 Jourdanes. Two of the stations were Astrid. One was a QH1. No, just a ZWO camera. That one's been published. That was a Bill Young, myself, and Graham Smith. We've got in progress 2 double stars and another binary asteroid. So how many chords? So how much is Astrid being used? So bear in mind, we've now got 60 Astrids in the wild. Most of those have gone out in the last few months. The number of chords of Astrid is ramping up. Norm gave me some stats for this month, the day before yesterday. So basically, Astrid is now responsible for 26% of the chords. And QHY 174 is 6% of the chords, and majority are the old analog 910 HX from Wattec. So comparison to the 164, the 174 GPS. So 174M GPS is more expensive, about double. It requires a lot of software. It requires a laptop, dedicated laptop for it. There's been firmware issues. It's closed source. There's occasional timing issues from it. It's just a camera. There's also a Gen 1 sensor. So Astrid kind of has all that beat essentially. Comparison to IOTA VTI. So the VTI is analog. Again, requires dedicated laptop. It's just a camera and time stamping and an analog sensor. And Astrid basically is a complete acquisition system.
Yeah, just to update that last slide, that $550, that's for the VTI complete kit with camera, cables, and everything, including the VTI itself.
Correct.
Okay.
So comparison to the GPS flasher. Also, is the VTI difficult? Do you have stock at the moment, or?
No, at the moment we don't have stock, and we're not sure if we'll ever be able to build any more.
Okay. So there's that problem too.
But there is a chance. I mentioned this yesterday. There's a chip to replace the chip that's out of stock and no longer being produced. That chip has its own font, and if the developers of the software that analyze the videos are willing to update their software to recognize the characters in the new font, we will be able to make analog VTIs again, and they will work. Bob Anderson has already indicated he would do that if asked. We haven't asked anyone else yet, so that's still on hold, but there's a possibility. So that's kind of good news.
Sounds good. So comparisons to GPS flasher, you've got to build it yourself. GPS flasher, you got to enter the times for the events. Oversaturation is a possibility, or undersaturation. It means you've got extra gear. It doesn't adjust for things like missing frames. It'll, essentially does the frame at the beginning, the frame at the end, but you don't know if you've missed frames in the middle. Well, you know if you missed frames, but you don't know which frames you missed and what the timestamp was on the ones you missed. The USB camera also has timing drift that you use with these types of setups, and also with the GPS flasher, there's lots of different versions of firmware out there. So it's fairly uncontrolled, and there can be issues with timing because of that as well. All those go away with Astrid. And for manual pre-point, you need star charts. You need to start at certain times. You've got a star hop. You've got a laptop, and it's quite a lot of time of frustration. I mean, I can star hop, but it's not the most pleasant experience, I would say. Although some people seem to enjoy it. Again, Astrid gets rid of all of that. So the current status is basically we have 60 devices out in the wild. It's been some of those have been supplied by me initially early on. Some of those have been supplied by Ted. It's been adopted by IOTA. There's units internationally in Spain, Australia, and Brazil already. So Astrid experiences. So I put a few things on here of things which kind of I've highlighted in green things which are to me struck me as one of the goals of Astrid, and that was show people get it right. So this one's from Tom Heise. He said Astrid gave me the confidence to know I was on target and on time for a successful observation. It's all become almost routine and relaxing once I'm on target waiting for Astrid to start recording. This is one got the other day from Greg. I've been using a Watt 120N video camera, IOTA VTI, SVID USB dongle on a laptop PC for almost 10 years. Many times I had to admit no observation because I couldn't get an integration setting and gain combination that would let me both see the dim and target stars and collect data at useful timing resolution with just a 5-inch aperture scope. That's from Chuck. The other one from Greg. I just wanted to report my first successful asteroid positive this morning. It was 100% unqualified success using pre-pointing. I was able to set up the pre-point about 5 hours ahead and then get some sleep before my alarm woke me up for the event. I was stunned at the dynamic range of Astrid recording. In my past experience, recording a Mag-12 event like this probably would have yielded something barely visible above the noise background, but Astrid recording was fantastically clear with an SNR of 6. This is a real opener, and that's from Greg. So the future. Autofocus. I've got autofocus devices. I've got a ZWO autofocus device that I'll probably one of the first ones I'll get working. Low level camera access, so I want to increase the frame rate to around 60, possibly faster, and I'm going to implement some lower level camera access to do that. Support for newer cameras and sensors as they become available. Multiple unattended automatic events in the night, i.e. complete automation, so load say 10 events onto there and then just have it do its thing during the night and pick up the results in the morning. So Astrid resources, if you want to order Astrid, you can order it from IOTA. It's $695 as of 28th September 2024. I believe the prime focus case is a little bit more. There's a QR code if you don't like typing things in. And documentation, here's a QR code for the documentation. So I try and document everything. That way I don't have to answer the same question 1,000 times, right? And also you get a faster response from the documentation. So there's documentation for most of the stuff, most of the questions on the website. I just like to say, basically I build the boards and cases and I send them to Ted, who then completes the intensive task of combining with the other components, assembly and testing. He's also added some finishing touches of his own to the devices. None of this would be happening without Ted. Bill Young lives in the same town as I do. He saw the vision from the beginning and supported the first units. His comments and feedback have been invaluable throughout the development. It's just a whole lot of fun for each of us to put down multiple cords on our deployments in Alberta. We have 5 Astrids each. Steve Preston has also been a great assistance with many discussions back and forth, which has led to a better end result. John Moore has been experimenting with cases and printing those off. Bob Anderson has been extremely helpful with many PyMovie and PyOT questions I've had. Haristo's provided and allowed the ability to download stations from OW Cloud to Astrid, which saves errors getting made when you transfer information. And Dave Herald has permitted the usage of his Tyco UCAC4 Gaia catalog in Astrid. And also to everybody who's sent feedback. You know, who already has an Astrid and has sent feedback over the number of months. So what's next? Shadow scope. So basically, my next goal is a custom telescope that's carbon fiber based. Has a f4 8-inch parabolic mirror. Is focal reduced down to f2. 3D printed, fully automatic. That includes a focuser and go-to. Designed especially for occultations, and is basically drop off and go. So we'll be able to deploy these in daylight, and then when it becomes dark, the device
I'm on it.
and configures itself automatically. And obviously, it's going to be powered by Astrid. And that's the mirror cell. It's got whiffle tree underneath and on the sides to remove any chance of pinched optics. And then this is it with the mirror in to show it. And thanks for listening. And are there any quick questions?
Thank you very much, Mark. And that's I sense that we are getting to the next step in the evolution of occultation observations. Sounds like we're making a real transition here. And I want to thank you especially for the innovations that you've devised for us here. I'd like to go on to the next talk, and I think that's Joan Dunham. Is that correct?
Yeah, I think so.
Okay. And take it away, Joan, whenever you're ready.
Okay. I think I'll get started. Did you turn off your volume?
I'm turning almost to zero.
Okay, let me turn mine up. All right. Okay. Now this is going to be somewhat. Let me do this first. Share my screen. Yes. There. Share. This is old-fashioned compared to Mark, using this guy, 14-inch, as an example. And let's see if I can get this to. Okay.
Slideshow.
I'm trying to get, it's got this button over the slideshow. I'm trying to get rid of it.